All right, if you guys remember, one of the last things I taught you before we last saw each other, or when we last saw each other, it was a balance beam. We could use two different masses, let's say maybe a 1 and a 2. Let's assume this is a meter stick, so it's 1 meter. And we saw that their torque's balanced. And I didn't really have to, struggle to convince anyone of that. But now, what we also want to look at is the forces involved here. There's a few forces that we kind of ignored here. We're assuming our pivot is centered at the 50 centimeter mark, and the meter stick itself has mass. So, we got a mass here, M1, let's call it 1 kilogram, M2, let's call it 2 kilograms. Makes sense as to why they're balanced if this is half the distance that this is away from this clearly defined pivot point here. Our force of gravity is going to be exerted right here on our meter stick. That's where the center of mass is. And we'll call the mass of the meter stick, I don't know, let's call it half a kilogram. So you got your three weights here, essentially. We'll write them down. If we're calculating the force of gravity here, we got 9.81 newtons here. 1 times 9.81. This one would be 19.62. And then we got 1 here, 4.905. Now, what we did not worry about was the fact that we didn't have to consider this because this generated absolutely no torque. Because its R value would be 0. It's got a distance of 0 meters from the pivot point. There's one other force we're not paying attention to here, and that's the normal force. This is a normal force acting on this object at that point of contact. And this force right here has to balance out 1, 2, 3 of these forces. Because if you think about it, our meter stick isn't moving. So it's in static equilibrium. That means the net force is 0. So if we simply write an expression for the net force, we have N up, force of gravity down, force of gravity down, and the force of gravity down. What I've done is I've shown you all 4 forces acting on the meter stick itself. All right, and now this is our only unknown. So if we want to solve for N here, we have all our numbers to put in here, and when we solve for N, see what we get. 19.62, 4.905, 9.81. N has to be equal to 34.335 newtons. So this thing is not moving up or down. It's in static equilibrium. And in addition to that, it's in rotational equilibrium. When you do the net torque, it does equal 0 because you consider this torque and this torque here. And what ends up happening is that you have this one would cause clockwise rotation. It'd be negative. This one positive. And these two are right on top of the pivot point. So we don't have to worry about it. So if we're looking at a counterclockwise one, it ends up essentially being 19.62 newtons. And that's a distance of 25 centimeters away. 0.25. This one's negative here. It's 9.81 newtons. And it is 50 centimeters away. And you know what? That ends up adding 0. And the torques are nice and balanced. But one thing that is, defined for us here is the pivot point here. We've got it balanced on this thing here, and it makes sense as to why that would be our pivot point. That makes sense as to why we'd choose that to be our pivot point. So this thing is in rotational equilibrium because we see these two torques are balanced. But a neat fact about an object in rotational equilibrium is that it doesn't matter where we define our pivot point to be. We can define it to be anything we want to be, and that wouldn't change what these forces are. These forces are what they are. Their values aren't going to change here. But let's just say I made some stupid decision here to make this my pivot point right here. Now I do know what my 4 forces are. So what I could do is I could figure out the torque generated by each of these forces. I could figure out the torque generated by that, and that. We have the numbers to do that. Well, let's just take a look and see what ends up happening here. So, weird thing about torque is the second you change pivot point, you technically change the value of the torque as well. And you might change the direction as well. Now, if you think about it, if we're pivoting around this point here, pushing up on this meter stick here, if it was fixed there, it would rotate it that way, counterclockwise. This one's a positive torque with respect to that point here. These three, on the other hand, would rotate it clockwise, so these would now be negative. So I've got one positive torque, three negative torques. Let's add them up. Sigma tau, what does it equal? We'll do the positive one first. We got 34.335. That is 50 centimeters away from this pivot point, 0.5. I've got this one as negative, 19.62. That's 25 centimeters away, 0.25. That's negative as well, negative 4.905. That is also 50 centimeters away. And the last one's a full meter away. So minus 9.81 times 1. When we look at all this, let's see what we get. It's going to take me a while to type it in. And hopefully I don't type anything in wrong. Perfect. The net torque ends up equaling 0. You can add up all these things and you can prove to yourself that the net torque is 0. If you're really looking to waste some time, if you're really bored, if you really have a lot of time on your hands, you can choose any other point in here to be your pivot point. You will get the net torque to equal 0. You can even choose this to be your pivot point, which will make no sense because it's not on the object itself, but the torque will end up being 0. Alright, so that's kind of a fun fact about rotational equilibrium. And that fact is probably going to carry us into how we look at some objects and analyze them from a rotational equilibrium aspect. So that'll be for another video. So I'm going to hit stop and